Good afternoon, everyone. I'm Lincoln Ding from the University of Minnesota. Today I will talk about my research on bio-electrochemical pretreatment of dairy manure for sulfide remediation before anaerobic digestion. Okay, so my talk will include the introduction of the hydrogen sulfide formation and removal, or lab-scale bio-electrochemical treatment, and finally the pilot-scale demonstration using our technology. So before talking about the treatment, we will first look at the hydrogen sulfide, or H2S. Hydrogen sulfide is an extremely toxic gas, and it's very corrosive with an acute rotten egg odor. When you peel the egg, sometimes you may smell it. That's hydrogen sulfide. And it's very dangerous even at a very low concentration, and it will be fatal once over 700 ppm. It's quite low, actually. According to the Bureau of Labor Statistics, hydrogen sulfide is one of the leading causes of workplace gas inhalation fatality in the United States. So hydrogen sulfide, H2S, is generally considered a safety hazard when dealing with organic waste containing sulfur. Sulfur remains in the dairy manure from the feeding material, from the bedding material like gypsum, and also the animal waste like the waste milk or something like that. And the sulfate-reducing microorganisms, including bacteria and archaea inside the manure, they will convert the sulfate into sulfide and finally release into the gaseous phase. So high hydrogen sulfide released from dairy manure storage, it's toxic to the workers and the cows, and it also reduces the lifespan of the facilities containing it. So currently, the easiest way to remove hydrogen sulfide or reduce it is increasing ventilation in the manure barns just to disperse the hydrogen sulfide in the air. For the anaerobic digestion system, usually the gaseous hydrogen sulfide removal is widely used, including the adsorption using ion-based adsorbents or the biofilters. Some in-situ hydrogen sulfide removal methods have also been developed, including the microaeration and chemical dosing, but usually they will require separate units outside the digester, which may increase the capital costs and the operational costs. So that brings us to our proposed bio-electrochemical or anode oxidation method. So here I listed 5 possible pathways for sulfide removal during the bio-electrochemical treatment. It kind of combines the activities of microbial and also the electrochemical reactions. So the first one is during the BEC treatment, the sulfate-reducing microbes will be inhibited a little bit. Second, the biotic direct oxidation, the microbes inside the anode biofilm will involve in the sulfide oxidation. The third way is the mediated oxidation assisted by the oxygen generated through the anodic oxygen generation. The fourth way is the direct or abiotic oxidation assisted by the anode itself. And the final way is the metal binding or metal precipitation. Because during the BEC treatment, the metal ions will be released through the anodic oxidation, and it will be combined with sulfide to form insoluble metal sulfide and precipitate in the sludge. So therefore, our goal is to develop a microbial or bio-electrochemical mitigation system for hydrogen sulfide released during the manure mixing and storage. So first, I will talk about our lab-scale BEC tests. These are schematic of the system. So we tested a 2-batch test. First of all, that's electroselection. So we want to compare the sacrificial and non-sacrificial anode material to see the effectiveness of the hydrogen sulfide removal and also its effect on the following biogas production. The second one is we want to see if we can separate the BEC system and the anaerobic digestion. So we can directly apply it in a short term and reduce the volume of the reactor. So this is the first test using the sacrificial metal anodes. So we tested including low carbon steel, LCS, aluminum, AL, and copper, Cu, against the titanium Ti cathode. So after the test, we can see low carbon steel and copper removed almost all of the hydrogen sulfide, but aluminum was actually ineffective in removing the sulfide. Then we examined the biogas production as well. Because the manure will be pumped to the digester later, so we do not want our anode to reduce the biogas production after removing the sulfide. So we examine the biogas production simultaneously, so we can see the low carbon steel anodes did not affect the methane production significantly, but they all reduced the carbon dioxide release. Aluminum was actually effective in facilitating the biogas production, but copper seems to be toxic to the microbes inside it, which reduced the methane production significantly. So when we combine the hydrogen sulfide removal and the biogas production, we can say low carbon steel is a viable a sacrificial anode material to achieve the two effects simultaneously. Then, because it's sacrificial low carbon steel, we want to see if we can replace it by some durable material. So it can stay in the manure pit for a long time without changing the anode material, without to add more electrodes. So we tested 3 different types of material, including stainless steel, SS, titanium, Ti, mixed metal oxides, coated titanium, MMO. So, but if we look at the results of the hydrogen sulfide removal, actually no or very limited hydrogen sulfide removal were recorded in all of the groups, which means these non-sacrificial metal anodes cannot remove the sulfide efficiently without the sacrifice or the dosing of the metal ions into the solution to combine with the sulfide. So pure anodic oxidation is not efficient enough to remove the hydrogen sulfide released from the dairy manure. Then next step, because for this experiment, we combine the BEC treatment and the anaerobic digestion together. But on the real farm, it's separated. The mixing tank and the digester is separated. In this way, we want to separate our BEC system and the anaerobic digester to mimic the real scenario. So first stage is the BEC treatment or pre-treatment of the manure in open air at room temperature for 24 hours. Second, then the treated manure will be subject to anaerobic digestion under mesophilic conditions. According to the selection of electrodes, we choose low carbon steel and stainless steel as the cathode. The applied voltage ranged from 1 to 2.5 volts for 24 hours. So we can see the manure became darker with the increase of the voltage here because of the formation of more black insoluble ferrous sulfide compounds. And this is the hydrogen sulfide and aqueous sulfide removal. So we can see all of the groups showed certain effectiveness in removing sulfide, but a low voltage of 1 volt is not efficient enough to remove all of it, while a voltage of over 1.5 can remove over almost 90% of the sulfide from the biogas. So then we look at the biogas production. Because it's not simultaneous, so the improvement in the biogas generation is limited also. The methane yields from all the groups, they are similar to each other, while the carbon dioxide yields were a little bit lower because of a reduced carbon dioxide contents. And more importantly is the technical digestion time, T80, which means the time required to produce 80% of the maximum methane yields. This T80 were reduced by 3 to 5 days in all of the groups, which means this the BEC treated manure, the AD process was accelerated or the efficiency is improved. So after that, we want to apply our technology into the real farm conditions. The question is how. So we designed and installed a larger scale one. So large pieces of low carbon steel anode and stainless steel cathode were mounted on a PVC holder, and a big box was built to separate the treatment chamber and the control chamber without the electrodes. Then we installed that in the manure pit, operated for over 2 months, and the hydrogen sulfide analyzer continuously measured the hydrogen sulfide levels from the 3 chambers, 2 chambers, the treatment chamber, the control chamber, and also the ambient air as a background. So that's the result. The hydrogen sulfide removal performance, we can see the BEC treatment reduced almost 80% as compared to control chamber without the electrodes. It also reduced 60% as compared to the ambient barn air. So another point I want to mention is that the temperature actually significantly affects the hydrogen sulfide emissions. So when it's winter time, the activity of the microbes were quite low, so which reduced the hydrogen sulfide emissions of all the conditions. But when it's summertime, the hydrogen sulfide levels needs to be taken care of more significantly. So then follows the question: is this technology economically viable? Currently, actually, during the manure storage, actually, I do not see actually use technology for sulfide control during the manure storage. So I have to use some technology comparisons from the literature. So we use our collaborating farm with 1,800 cows as an example, and the operation period was 10 years. So that's the overall cost comparison. So we can see actually the ferrous chloride dosing shows the lowest overall cost as compared to all the other methods. Our BEC treatment, however, is still cheaper than ferrous chloride dosing and or iron oxide dosing. But these costs does not include our benefits. The BEC's contribution to the biogas production is not considered here, and the oxidative stress posed by the ferric chloride dosing is not also considered here. And we still can improve it by trying more different configurations. So it has plenty room to improve. So to summarize, our lab scale BEC treatment significantly reduced the hydrogen sulfide emissions by over 90% from the dairy manure. Sacrificial metal anodes, low carbon steel, are most effective in hydrogen sulfide removal with improved AD performance. Our pilot scale results confirm its feasibility of the system, and with up to almost 80% of hydrogen reduction. It's a little bit lower than our lab scale test. The long-term costs are still competitive, making the BEC treatment more promising to chemical dosing. Okay, that's all. Thank you.